In this case, we cannot build a linear programming model as the one we created for the Acme case. And the main reason why this is so is because of the variability we have regarding inter-arrival time between customers, the serving time, and the income per customer. And because if we try to work with average values, we would have the same effects that we had with Bob and Ray, because we cannot take for granted that we are going to have 30 customers per hour, 2 minutes apart from each other, because that might not be the case. Sometimes we will have a few customers arriving in a short period of time, and some other times we will have them not arriving that close to each other. And if we're assuming that they are arriving exactly every 2 minutes, we will be overestimating our capacity, and we were assuming we're making more money than actually we're going to make if we implement this decision. So we cannot work with average values. And if we try to use the optimization or linear programming approach that exists, that takes into account stochasticity, I won't get into all those details, but that might lead us to a problem that is far too complex to be solved, and it is what we call an intractable problem. So there is no way for us to represent this variability into a linear programming and to have something as elegant and efficient as we had before that gives us the right combination of the number of employees and dispensers. So instead of that, we are going to use discrete event simulation. So this is a mock-up of how an environment works, which I'll show later on. And what we have here is the core of how a discrete event simulation model works. So we have here a graphical representation of our system. We have two dispensers, we have a queue, and we have the operator. And we're going to see here an animation of how things are in our system, as you most of the time see when you build a simulation model. You have a clock because you need to keep track of time and see how things change as time advances. You have the states of the elements in our system. You have the operator, which is idle, the dispenser, which is free, the dispenser 2, which is free, and the queue, which is empty. This is how things are at the beginning of our, imagine that we're opening our gas station at 7 o'clock, and this is how things are. And this is a table where we are going to log the time, the events that occur, the new events that will be generated, and how things change in terms of the operator, the two dispensers, and the queue. So simulation or discrete event simulation consists in reproducing the possible behavior of the system. In the Bob and Ray case, we have that in a table, and we also have that in tables in a more complex manner. But what happens in both models is that we are going to reproduce possible behaviors of the system, generating different random numbers that will lead us to different events. And if we replicate that a large amount of times, or a sufficient number of times, what we will have is an average estimation of how our system will behave if we implement in our real system what we are trying in our model.